So I think we'll go straight to Sophia, if that's okay. Thanks, Phil.
Okay, thank you very much. Hello, everybody. My name is Sophia, and very nice to meet you all. I'm just delighted that I have a chance to share with you a little bit about my journey to become a scientist and to work on antibodies for cancer therapy. So we are very interested in antibodies because we naturally produce them in our bodies to protect us from infection. But interestingly, our body also makes antibodies that can recognize and destroy cancer cells as well. And we have developed technologies in the lab where we can actually create antibodies by looking at just the code, the genetic code of an antibody. And I'll tell you how I arrived at this type of work as a scientist. I'm actually originally from Greece, and we moved in the United States with my family. My father was serving as a foreign consul of Greece abroad in New York, and this way I was able to graduate from my secondary secondary education from the United States, from New Jersey, and I was accepted and entered Rutgers, the State University of New Jersey, which is a beautiful and very big university in the United States. It has a big focus on biotechnology and developing novel therapies for different types of diseases. So I was very early interested in this concept and how things that we do in the lab and how things we learn in academia, how can we bring them to the patient. I studied under the supervision of a very encouraging and very inspiring professor, William Ward, who actually passed away only recently. I was inspired to try to understand how proteins in our body talk to each other. And from there, I developed an interest in antibodies, and I had the opportunity after I graduated in 1991 with a first degree and a master's in protein structure to be invited to come to London to work with Professor Hannah Gould and Professor Brian Sutton, who are interested in B cells and antibodies of the IgE class. It's a special class of antibodies that we have in our blood, and how these can trigger allergy. So soon I developed a big interest in antibodies. And what do they do? Are they pathogenic? Can we change that? Can we re-engineer them and change them to make them therapeutic? And during the time, I also received a scholarship with GlaxoSmithKline, and I spent about a third of my time during my PhD working at GlaxoSmithKline on site. So I had the opportunity to meet some very exciting people and very inspiring people who understood therapeutics. And again, I was very much inspired to work on a therapeutic angle of my studies. So after that, I spent a bit of time working as a postdoctoral scientist. I received my PhD in '95, and then I moved to UCL, the University College London, and also I worked for a while for a company in Cambridge, which was spun out of GSK. And some of the people who opened the company knew me when I was a PhD student, and they were very interested on my skill set. So I interviewed and I entered to work for the company for a couple of years. And also during that time, I really felt that my big love was antibodies, and I had an opportunity to go back to King's College London with Professor Hannah Gould. And at that time, I started developing the idea that perhaps I can design my own antibodies and lead my own program of work. And Professor Gould was very supportive of this. And she promised to me if I came back, we would consider how I can open my own group and develop my own interests. During this time, while I was working as a postdoc, I worked a little bit in vaccination, and my interest was in cancer. So I was very much interested to find out that people who had melanoma, patients with melanoma, didn't do very well in the clinic. There were no drugs for them. But if you triggered an immunotherapy response by giving them antibodies or other drugs, maybe these patients could do better. So I made it my life's mission to do something about patients with certain cancers that are not curable. And during that time, I met some very clinical colleagues, including Professor James Spicer, who headed the early phase clinical trials at Guy's and King's. And during the time, I was also able to tap into an opportunity because at King's, for the first time, the National Institute for Health Research offered the possibility for
Sophia, I think you're muted.
Hello. Oh, okay. I don't know why that happened. I think it said host muted me. Okay. Can I continue now? Is that okay? Can you hear me? Yes?
We can hear you great, Sophia.
Okay, excellent, excellent. So in 2007, I was offered, even 6, I was offered the chance to apply for a small scholarship on a personal level to support myself and to be given the chance to open my own group. I applied and I got the chance with a small amount of money, to launch my group. And I decided that we will focus our work on trying to understand how our immune system works, why the antibodies we naturally produce do not protect us always from cancer, and how can we make antibodies for cancer therapy based on this knowledge. So I received this fellowship, and then in 2013, I was appointed to a permanent position at King's College as a senior lecturer. And then I was promoted to reader in 2016 and a professor in 2019. As you can see in the bottom of the slide, that came as well at the same time as raising a family. I have two children, and this was all a juggling act, trying to be a mother, to run a household, and to lead a group. From 2008 onwards, I started receiving some funding. I worked very closely with colleagues at my university, and we together applied for certain amount of money, which could help us to develop some of our ideas. And one of the ideas was supported by Cancer Research UK, which is the charity we all know has a big foothold in cancer therapy and study and research in cancer, but also helping patients. And with their support, we were able to arrive to a clinical trial of our first idea for our first antibody therapeutic agent. And from there on, I also considered that perhaps in a clinical trial, I can help maybe 10, 20 people, but maybe if I made a therapeutic pipeline of drugs, I can help thousands of people. So I spun out a small company from King's, which I am a founder, but I do not work for the company. I support the company and I do experiments for the company, but I allow them to launch a business program while I'm studying and supporting the science of the company. Just to give you an idea a little bit about what motivated me, you can see here from the Cancer Research UK website that 10 key ways by which cancer cells are not the same as healthy cells. And from all those 10 things, what really sinks to my heart is their ability to hide from the immune system. And I have made it my life's mission to turn the tables on cancer, because our immune system protects us from many things, from different pathogens, but also protects us from cells in the body which go wrong and the immune system destroy them. So when a cancer cell develops and the immune system doesn't see it anymore, what has gone wrong in that process? So I'll show you here some pictures. I don't know if you can see my cursor. This is the success of drugs from the moment that they have been approved to go into trials to be tested in patients until they become a drug that is given to every patient in the world. And you can see oncology here has a very bad success rate, something like 5% of the drugs that start from a lab until they are approved for treatment of patients. Only 5% of them, so 95% failure. However, when I look at a melanoma tumor, you can see here a melanoma tumor. In the middle of the tumor, the black here is the cancer. In the middle, you see this area where the tumor has been cleared. And the thing that cleared the tumor is the immune system. So really trying to understand that balance between how the immune system works to kill some cancer cells, but how the cancer cells stop it from becoming very effective. And this is what motivates me. So one of the things that we look at, and I think we all know that our body produces antibodies, but the antibody factories in our bodies are the B cells, the B lymphocytes. They can be triggered. They can see external pathogens. They can pick them up and they can make antibodies in response to that. And antibodies are really very special because they have two regions that are key. One is what we call the Fab region, which is the region that binds to the antigen. And it binds to the antigen very specifically, like a lock and key. Only one key is recognized by one lock. So it's very specific for a specific molecule. And this molecule could be on a cancer cell or a pathogen. The other side of the molecule, what we call the Fc, is the handle which brings in the immune cells. So if the immune cells are recognized by the Fc region, by this part, the handle, and the Fab is recognizing the cancer cell, what you can have is this. So the antibody is made by the B cells. It comes to recognize the cancer cells. It can bind very, very specifically with a lot of force, what we call affinity. And you can actually see that the cancer cell can be destroyed in that process. And one of the ways by which that happens is through the handle, because the handle brings the immune cell. The immune cell recognizes the cancer cell, and the handshaker is the antibody. And then the cancer cell, the immune cell secretes all these toxic molecules that actually destroy the cancer cell. However, we found in our bodies, in our studies, that in our bodies, we make many different types of antibodies. Some of them are to enhance our immune response, and some of them are to dampen our immune response. And what we found in patients is that a specific antibody class called IgG4 is the one that's preferably produced in tumors. And this antibody class is known not to be very effective in making this handshake between the immune cell and the cancer cell. And we found that the more of these the patients had, the more likely they were to do worse. So the high amount of this inflammatory and not effective antibody, the quicker these patients died. So we really were trying to understand more about why our immune system is not making this important connection between the immune system and the cancer cell to trigger the death of the cancer cell. So we use this information in our lab to try to do many things. We can manipulate this handle of the antibody, and we can then make this handshake between an immune cell and a cancer cell very effective, and we can trigger immune clearance. So where the immune system is off, we actually can turn the on button. And this is what we try to do in our lab. And we can do this quite successfully. I think I missed this part, sorry. So because we can do this, we study the tumor. Here is some a representation of a tumor. You can see cancer cells here, and you can see immune cells, you can see antibodies, and you can see different molecules that the cancer cells and the immune cells produce that change the environment and take away the strength of the antibodies. So what we can do, we take that information and we can actually engineer antibodies that can overcome these negative signals that the cancer cells give to our immune system. And this way, as you can see here in this tumor lesion, it's a slice of a tumor, and in green you can see the cancer, and in red you can see the immune cells. And what we've done, we've added an antibody that actually brings these red cells from the outside, and you can see here some of the cells on the outside, into the tumor. And this swimming of the cancer, the leftover cancers inside this immune cell infiltrate is triggered by an antibody. And when you do that, that means the tumors are really shrunk and they really are constrained by the immune system. And this work has actually been, has resulted in a clinical trial, which is now almost to its end in patients with cancer, and which reported this year some interesting results, showing actually a patient who has already responded to this treatment. And these ideas have also gone back into us designing special assays that are accompanying this trial and help the clinicians to decide how they can treat a patient. Is it safe to treat the patient? Can we select the patients who are more likely to respond or are not going to see any toxic effects from the drug? And all this knowledge we receive goes back into the lab, and we can study more and try to understand better how our immune system works, how antibodies engage with that immune system, and what can we do to make our drugs even better. And just to, I think my computer is causing me a few troubles, but I hope you can see the last slide, because to me it's the most important slide, because it lists some of the people in our lab who work to make this thing. Our lab works by bringing in scientists, basic scientists, clinicians, young clinicians, more experienced clinicians. You can see here a list of people in the clinic who are actually very engaging with us, working with us, advising us, and helping us to think about the patient treatment. And young clinicians bringing that experience back into the lab and discuss with our basic scientists. And all together, we go from discovery, understanding what happens in cancer, and to designing our own drugs and find out how they work. And we find out whether this can be given safely to patients. So then we can do clinical trials and eventually into a commercial space where we can actually roll them out, like hopefully we'll roll out the vaccines for COVID for many, many people, millions of people out there. Our work hasn't just been good for patients, but it's been good for science, because we actually have our work on understanding how antibodies work and how we can engineer them has resulted in a new field we call allergoncology. This field has inspired many other scientists. You can see our group here in Vienna and here in Barcelona and here back in London with a very big professors from all over the world who come together and think about how can we do better for patients and how can we understand our immune system and relate it to what can we do for cancer patients. So all these people that you see here are really special. They work really hard and they come from a variety of backgrounds and from across the globe. We are very international. Most scientists labs are very international. So we have a team from everywhere in the world. I'm not sure we have a continent we have not represented in our group yet. And here I've shown you a list of some of the people who graduated and went on to do new things. Some of them have become important people in the biotechnology industry and the pharmaceutical industry. Some people went back into academia. Some people went to the clinic and became consultants and clinical lecturers. So we have a variety of career paths after the lab has trained young people. This is very important to me. It means a lot because it's not just about developing fantastic therapies. It's about inspiring the next generation to do even better things than we can do. So I think I'll stop here and maybe I can take some of your questions. And thank you very much for listening.